Hello everyone. I want to pick up talking about one of my favorite topics on tree rotation. So just to review real quick what we did in class today, I told you how if we have a tree that looks like this, or even if we're in the middle of a tree that looks like this, we can reconfigure some of the child relationships to get a similar tree, which has the exact same in order. And so here I'm using these little symbols here, the triangles A, B, and C, to indicate any subtree. And I'm leaving it totally open what those look like. They could be huge trees, they could be a single node, they could even be nothing. But it's important that I at least have this node X here, which is a left child of the Y. And that's really what I need to continue with this. Okay, so what I'm going to do a clockwise rotation about the node Y, that's what we call it, clockwise rotation about Y, is we are going to promote X actually to be the root, and then we're going to move Y down, and we're going to move C down. B is going to stay where it is, but A moves up. So if A happened to be heavy, so the height was much larger than it was in C, this would be a good move, because we'd be moving A up and we'd be moving C down. It didn't matter so much if C was lighter. So this is a way that you can rebalance trees with this operation. Another way to look at it is, personally I like to look at it from the bottom up actually, even though I just kind of defined it from the top down. What we're saying is I'm going to pair A and B together over here before I pair them to C, if I'm building things from the bottom up. Over here, though, I paired B with C before I paired the result to A. So that's a difference there. This is actually the exact same thing as thinking about making parentheses. So here I'm saying I want to put A and B in parentheses together. So if you're thinking order of operations here, I'm going to put A and B together before I put them with C. Whereas over here, I'm saying I want to put B and C together before I put them with A. So actually, you can describe binary trees with parentheses, systems of parentheses. So that's one interesting side note there. Now notice, regardless, in the trees, if I do an in-order traversal here, so I say go through everything in tree A before I go through X, and then B, and then Y, and then C, well, the in-order traversal is preserved over here. So the in-order traversals are the same, even after this clockwise rotation about Y. So I go in order here, I say, okay, I want to go through all of Y's left before I go through Y, which recursively I say I want to go through all of X's left before I go through X, before I go through B. Now I'm back up to Y, and then I go to the right. So that is A, X, B, Y, C. And the same thing over here. I go A, X, and then down here, B, Y, C. And remember, another way to understand in-order traversal is I draw this lower envelope below the tree. So it's sort of like this little almost silhouette that I can draw below the tree. And it would be the order that curve visited things. So I can see A, X, B, Y, C. And over here, similar. Even though things got swapped around a little bit, I still go A, X, B, Y, C. So anyway, the upshot of all this is I have two trees which are different, but which represent the same information, the same sorted elements that are stored in this tree. All right. So this is called, again, a clockwise rotation about Y. So I'll just denote that for now as CWY. Now, I personally don't love this terminology, but that's what people call it. So that's what we're going to call it for now. To me, rotation is like a weird word in this context. But I guess you can kind of think of it as like somehow rotating Y down a little bit and then bringing X up. If you were to follow Y as like a clock hand. Okay. But anyway, this is an invertible operation, so you can go the other way. And in this case, it would be called a counterclockwise rotation about X. All right. So that's the full picture here. Now, just to review how this is going to go with the pointers, we also talked about this in class. So for a clockwise rotation, we would have to modify a couple pointers here. So what we would say is, okay, let's let B be. So okay, first of all, it's important that y's left child actually exists. So I'm going to say assert y.x. So what this means is, assert y.left. So y actually has a left subchild, or left node, a left child. So that's important. Otherwise, this doesn't make any sense. Okay, so assuming that y actually has a left child, then I can say the following. Okay, well let me let b be, or I'll let x be y.left, and then I'll let b be x.right. All right? And now, okay, x's dot left is still going to be a, but now x's right is y, actually, right? And also, y's left has changed to b. But that's really it. So, and then what I have to do is I'll say, okay, root of this subtree, this entire subtree, becomes x, right? So x now moves to be in the root. So those are the steps that you have to do there. Now just to show you, I can do this in code. Let's put them side by side here. So I'm going to play a similar trick to what I played in the tree removal, where I'm going to say, all right, I'm going to kick this recursion off here. So I'm focused on the clockwise rotation now, CW. Let's say I'm going to rotate about a node with a particular key, clockwise. And so I'll do the thing where I say, okay, self.root equals self.rotate, and that's so I don't have to keep track of parent pointers, but I can actually reassign children recursively. So this is how I kick off the recursion. And then, okay, so I have a helper method up in the node class. And at first, I just look through and I say, okay, if I haven't found the key that I want to rotate around yet, I'm going to search for it. So if the key I'm looking for is less than the key at this node, I'll recursively go to the left. Now, importantly, I'm going to do this reassignment, right, just in case the root changes. So just in case the root of this left subtree happens to change during a rotation, I'll be sure to reassign it. And similar thing for the right subtree here. Oops, I'm looking in the CCW. Okay, I'm jumping ahead of myself. So going back up to the CW one, okay, I say similar thing here. I say, let's assert that y, so y in this context is self. Okay, so let's assert that y.left actually exists. If this is null, then this is not a valid operation. And then I'll do exactly what I wrote here. So b is x.right, and then I'll say, well, I did these in a slightly different order, but everything is pretty much the same here. And so to make the new root of this tree be x, I'm going to return x now. That's what I do. Otherwise, if I'm not doing a rotation, I'm not reassigning a root, I just return myself. Okay, so that doesn't change any of the relationships. Okay, so here it is in its full glory. Maybe I'll rearrange this so it's actually looking exactly the same. Self.left. Okay, cool. So I got b is equal to x.right, and then x.right is equal to self, which again, self is y in this context. And I think that matches exactly. Okay. Now it's a similar story for a counterclockwise rotation. I won't bore you with the details now. I'm sure you could do it yourself. But here's what I want you to do now. So I've constructed a tree down here. It's what I get when I use the add method that we defined to add the keys in this order. Okay, so I'm adding 15 keys between 1 and 15. So with that exact number of keys, my tree can be perfectly balanced. So it can have one node at the root, and then 2 nodes at the next level, and then 4, and then 8. So it's actually possible that it can be perfectly balanced. But here this tree is quite unbalanced. And so I want you to see if you can start with this tree and do a series of rotations to get it balanced. And I want to see if you can minimize the number of rotations. So just a little exercise to do before class. See if you can get it balanced. Don't spend more than like 20, 25 minutes on this. But I do want you to try this because it's kind of an interesting exercise. So just to show you how to get started here, I might say, all right, let me do let's say I want to do maybe a counterclockwise rotation about 8. Let's try it. So I'll say t dot rotate ccw 8. And then I'll make a new figure, and I'll draw the tree after that. And so there was the result. So I did a counterclockwise rotation about 8. That moved 8 down. And then swung 9 over there. So that, I don't know if that was helpful or not, but that's what that did. Just for another example here, let's say instead of counterclockwise rotation about 8, maybe I did maybe a clockwise rotation about 4. Let's see what that looks like. Okay. So again, I don't know if that was particularly helpful, but I would like you to experiment with this and see if you can get it to be balanced if you keep doing this. So maybe here I rotated about 4, but I can do something else now. Maybe I can now do, I don't know, a counterclockwise rotation about 10. And I'll draw it again. So it doesn't really seem like I'm helping that much, but that's up to you to figure out. And I have a program that actually computed the best answer here, so we'll compare notes in class on Wednesday. All right, see you then.